All right, guys. So as we wrap up 4.1, I remember in the last video, we talked about finding extreme values, absolute maxes, absolute mins. We defined them. We talked about critical points, and today we're going to wrap things up with, I promise, a shorter video for this part to look into how to find local extreme values. So we talked about absolute maxes, absolute mins. And now we're going to be talking about local maximums and local mins, or also sometimes called relative extrema as well. Okay, so first and foremost, I want to give the definition, and then I want to put it into a graph to kind of simplify the definition a little bit more so. So let's say, for instance, we have a value c. It's a specific x value c, be an interior point of the domain of the function f. All right. If this case happens, then c would be considered, or f of c is considered a local max at c if and only if the value of f of x is less than or equal to f of c for all x in an open interval containing c. So, I mean, think about what it meant for it to be our absolute max. If f of x was always going to be less than f of c, then it's a maximum value. Well, this is the exact same concept with local max, except we're now talking a specific interval containing a point C. So we might find another little area in there in which we could have a local max and a local min. Basically, what I want to kind of reiterate here is local max and local min is kind of the, let's put it this way. The local max, let's say, let's put it into a neighborhood. Okay, let's think about a neighborhood for a sec. Let's say, for instance, you have the biggest house in your neighborhood. You would have a local maximum house for that neighborhood. But let's take into account your town. Let's say your house is not the biggest house of your town, then it would not be the absolute maximum. But if you kind of contain the interval to quote unquote your neighborhood and you have the biggest house in your neighborhood, you would have the local maximum. But then for your town, if your town is the interval, the entire function itself, then your town, you would not have an absolute maximum, just that local for your neighborhood. So hopefully that kind of helps you kind of put it into perspective a little bit as well. So there's a relative extrema. Also, you might hear it called, local, relative, absolute, global. Let's do a graph real quick, guys. So I'm going to keep it, pretty simple. And let's just say we have our x-axis, and I guess I can make a y-axis too. We have our x-axis down here. And let's say, for instance, we have a graph that looks something of the nature. I'm not really caring about what the y values are right now. I just want to show what it means and what it looks like to be local versus relative, or local versus absolute, and then see how we can use the derivative in an example to go ahead and find the local extreme value specifically. So let's say, for instance, here the graph looks something like this, and then comes up, maybe a cusp up there, and then comes on down as we go through. And so, kind of looking specifically, we see the lowest point on our graph is going to be right here. This would be considered an absolute minimum. It's our lowest point. But let's say, for instance, that we are concerned with the interval. Let's put some values here real quick. Let's say this is a point A. There's a point B right about here. Here's a point C. Here's a point D, and so on and so forth. And so if we're looking specifically at an interval from A to C, we would have a local maximum right here at the point B. So this would be considered a local maximum. Likewise, let's say that we are looking from B to D, looking at the interval from B to D. This would be considered a local minimum. And then now we're looking at, well, here's our absolute highest part of the graph. And so this would be considered the absolute maximum. So kind of relating back to our entire thing, the town is the entire function itself. The biggest house on in the town is found right here at our absolute maximum. The smallest house of the town is found right here at our absolute minimum. Let's say now we're talking about a specific neighborhood on a block of, a random gated community that we're talking about here. We'll call it Fawn Lake. So we're looking at the Fawn Lake neighborhood. The biggest specific house in Fawn Lake neighborhood, which stretches from A to C, would be found right here. Let's say we have another neighborhood called Fawn Ridge, and that neighborhood stretches from B to D. That would be considered finding the smallest house would be right in there. Again, hope that kind of helps us out to see the difference between them a little bit as well. So we have a little theorem we want to talk about when we're talking about local extremes. This will help us use the derivative to find local extreme values specifically. So the first thing that we're looking into, if they'll load up, if we have a function f. So if a function f has a local max or local min value at some interior point of the domain C, then we can say what's going to happen with the inner or the derivative is what's interesting. And so if this is the case, that if f prime does exist at C, well then what should happen is that f prime of C should end up equaling 0. So if there is a local max or a local min, we can for sure tell that as long as the derivative is differentiable at C, all right, that is the function differentiable at C, then what we're going to see is that the derivative actually is going to be equaling 0 at that point, x equals C. So let's kind of put that into a little bit more perspective of finding it all. So in this example that we're going to be doing into finding the extreme values of f of x, and we're talking absolute minimums, absolute maximums, local max, local min, and once again, we can do these things graphically by just, substituting them into the graphing calculator. But let's say, for instance, that's not an option for us. That's what we're going to take a little bit of time here to look into. If my OneNote will pop back up. I'm having some bad luck over 4.1 so far with OneNote, so we'll get this rocking here in just a sec, guys. I apologize. All right, we're back on. So let's say we want to find the extreme values. So let's find all extremes of the function f of x equals 1 over the square root of 4 minus x squared. So we're concerned with all of the extrema for this one, local max, local min, and all the absolutes as well too. So first and foremost, we gotta kind of think for a second as to where is this function actually going to be defined. Well, because there's a square root in the denominator, we know what we have to have is that 4 minus x squared must be greater than 0, so we don't have that negative in that square root. And so when you solve specifically for this x, you see that it has to be from -2 to 2. Solving for x, just adding the 4 on over, divided by -1, and so on and so forth. Remember, the reason why this is going to be the open interval from -2 to 2 and not closed, because you also can't have 0 in the denominator of the entire function as well, and -2 and 2 would cause a 0 in the denominator, and so that's why we can't include those specifically for it. So let's go ahead and find the derivative of this function, because we know we need that to find absolute maxes and absolute mins, and according to our theorem we just found out, also our locals as well too. So first and foremost, f prime of x. Let me switch this up a little bit. Let's kind of recall that this actually is the same thing as the function of 4 minus x squared to the -1/2 power in here. So that's just going to make things easier to find our particular derivative. And so find the derivative here. We have -1/2 being multiplied by 4 minus x squared, and -1/2 minus 2 over 2 becomes -3 over 2. And then don't forget, we have to multiply it by the inside of that function. So this is kind of our chain rule. So we need to multiply it by the derivative of 4 minus x squared. So the derivative of 4 minus x squared is just 2x. So simplifying this out just a little bit more so, we end up getting x on our numerator, 4 minus x squared to the 3/2 power, keeping the powers positive. That's why I put it back in the denominator here. So now, kind of, looking specifically, we got to find where the critical point is going to be. So remember, that critical point specifically is where does f prime equal 0, or possibly where it does not exist, okay? And so between -2 and 2, the only point we're going to have a problem there is going to be at 0, right? So that's the only time specifically we're going to have an issue, is going to be at x equals 0, because when you substitute 0 on in there, we have some problems when it comes down to, because f prime equals 0 at 0. So let me kind of show this real quick. F prime of 0 equals 0 in this particular case. But remember, this is what f prime of 0 is. To find where the value is, I need to find out where f of 0 is, not f prime. So f of 0 is just really 1 over the square root of 4 minus 0 squared, or 1/2, okay? And so this is a good opportunity to look for a extreme value in this example. So what we need to kind of look a little bit more so into it, we got to see a little bit as to what's happening around the point at 0, okay? So as x moves away from 0, either on the left or the right side, what's happening? Well, the denominator is getting smaller as I am either getting bigger than 0 or if I'm getting less than 0. And so if that is the case, the denominator is getting smaller, the values of f are increasing, and the graph is going higher and higher and higher, because that denominator is getting smaller and smaller and smaller as I am adding some more, values to it specifically. And so when this happens, we know the graph is rising and we have a minimum value at x equals 0, and the minimum is the absolute, because there's going to be nothing else, particularly in the function as well. And because we know the function itself is going to kind of continue to rise and continue to go and go and go, we're not going to really have any maximum values that we are dealing with when this is all said and done. And so when this kind of comes to an end, we know that we are going to have that minimum absolute value, the absolute maximum or minimum value at x equals 0. So we have the absolute max at, min, absolute min at x equals 0. And so we saw that f of 0 was at 0, 1/2 is where that absolute minimum value is going to be. And because it's constantly rising as x gets away from 0 and either the left or the right hand side, that denominator gets smaller, so we get to see that the graph is going to rise, and obviously it's going to go off into infinity, and so on and so forth. And so this kind of shows us that that's going to be our really only point that we can have in this example that we're dealing with here. So that's all we have. That's all we have, the absolute minimum. We don't have anything that kind of goes with our extreme, our local extreme value theorem or anything like that. So this is, it kind of is what it is for this particular example here. That's kind of wrap it up for us, guys. Hopefully that example helped a little bit in looking into these. And other than that, I want you guys to give one more shot on your own. So what I want you to look at is find all extremes. You're going to do find extrema for g of x equals e to the negative x over the interval from -1 to 1. And to check your answers, you're going to see a max absolute. You're going to find an absolute max at this one at the value of -1 e. You're going to find a minimum value an absolute min when x equals 1, and the value will be at 1 over e. So at 1 and 1 over e for this particular example here, okay? Give this one a shot, guys, on your own. Double check your answers, and on to the next one.